Right. So my time said it's 6:12. Maybe we can start. Bill, you want to share the screen? I need to get off my screen.
Oh, okay.
Hey.
You can switch to speaker mode and you can see the full. Okay.
There we go.
Okay.
So, can you hear me? I'm
Yes.
not muted.
Yes.
All right, good. So, we'll just kick it off. Consultants Network is one of the co-hosts of this session tonight. We try to promote the development of our members' careers with a lot of social networking, which, as Kai has just been talking about, we hope to get going again in April. Publicize members' skills and link you up with IEEE. And we do have to point out that it's IEEE that makes this possible. We are part of that organization. It's a global organization. I think it's maybe 430,000 members now, over 160 countries. You can find people in IEEE who can help you advance your career. It's one of the best reasons to join. Another reason is to get access to all of these refereed publications at a reasonable price. You know, you can buy these articles without joining IEEE at an unreasonable price. And then more than 1,800 annual conferences, WCNC being one of them. Kai will talk about it a little later. You get a significant discount in registration fees for the conferences if you're an IEEE member. And will it advance? Yes, have to tell you who our people are. Luis Basto is trying to retrieve his wallet. He's our chairman. Jody Everett, our vice chair and treasurer. I'm the secretary of CTCN. Kai is the member at large, and Kai is actually the person who carries most of the load in finding speakers for us so that we can have monthly meetings. And Sergio Lieberman, a member at large. If anyone out there wants to volunteer, we need program chair to help Kai carry that load on finding speakers, and we need a webmaster. Our website is pretty old and decrepit at the moment. It's functional, it does the job, but it's not very inspiring. We could use a webmaster to help us upgrade that. So that's all I'm going to say, because the
IEEE R5 co-host meeting. The host composed of 4 Life Member Affinity Group. That's Central Texas, Denver, Houston, and Kansas City. And we have 2 Central Texas chapters. One is Electron device, which head by our leader, local leader, Larry Larson, and Concern Network, led by Lewis. So that's page 1, page 2, page 3. So that's our organization. And that's our plan for the year. And we need your input, topics, our suggestion for speakers and topics. And we need more live member participation. And the topic we're interested in are technologies of all type. And we want to look at our hobbies, travel, education, finance. And I want to hear your story and your contribution, and health, aging. I want to see the history and in the engineering and science area. Okay. So this for a forecasting. In April, we'll have a gentleman from TUV to talk about product safety. In May, and we have a lady talk about AI-driven SaaS 3D conversion product that her company is introducing. Some upcoming events. In April 10 to 13, we'll have a wireless communication and networking conference to be held in Austin, Texas, in Hilton Hotel, and he's the website for more information. If you do a Google 2022 WCNC, you'll find us. And we need volunteer. We need people participating in this this event. Austin is opening up. We just had a South by South event starting 2 days ago, and we see a lot of people coming in from our town. So the city is safe. We're in stage 2 now, and please join us. And the next item is April 1st to 3rd. We have a IEEE R5 and Green Tech conference in Houston. Also in a Hilton Hotel close to the airport. And here's the link, IEEE Green Tech. You can find us. And one particular interesting thing is we have a student robotic competition, and it's held underwater. So you need a swimming pool to do the Zoom competition. For tonight, the topic is Moore's Law, and speaker is Dennis Ferguson. He's a IEEE senior life member. He's a microwave and analog engineer, which is very few in this country. And his career is started in Honeywell, Minnesota. He worked on MMIC and RFIC area. And later on, he went into startup business, few startup tech company, both in Florida and Texas. One of that is developing a clockless logic. And he sold his company in the last company in 2014. He's semi-retired. He's currently working on some software for the Mac OS and iOS. And he held 8 patents, and he published 38 papers. And his background is bachelor's EE at UT Austin and master's degree from the University of Minnesota. And probably already read that the topic is a Moore's Law, and you talk about, probably already read the introduction earlier in the web page. I'm not going to spend more time here. Oh, Dennis, please search your screen and give your talk.
Y'all can see it?
Yes.
Yes.
Okay, so thank you for that introduction. And there's a lot of slides here, and we might as well launch into them. Maybe. What's wrong here? It's not going. Oh, here we go. All right. So you should see a new slide, correct?
Yes.
The presentation goes, okay. There's a lot of work that's been done. I mean, a lot of presentations and reviews and what have you on Moore's Law. In fact, in the next slide, it'll talk about the fact that if you do a IEEE search, there's something like 16,000 different references of journal articles and presentations and what have you. So I've been involved in this industry for since the mid 70s, the late 70s, and then particularly since the early 80s. And I've kind of grown up with Moore's Law, so to speak. And usually people talk about it from the classic transistor scaling, but they're not really talking about transistor scaling. What they're really talking about is the fact that the devices became more powerful and it improved productivity. More digital stuff things got built. So what I wanted to do is kind of cover transistor scaling to a small scale and make some observations on that. I also wanted to cover chip building. You don't normally see that in these presentations on the things that have been done in order to facilitate Moore's Law on a chip building level. And then finally consider the economic impact on productivity, and then at the end make some projections on the near-term future trends that are likely to occur, and then, maybe make some projections on how the industry will unfold 20 years from now when Moore's law is definitely dead, because, you cannot shrink things past the level of an atom. So at some point it will die, but it depends upon how you choose to interpret Moore's law as to whether or not it's really dead or not. And there is a thing called Amara's law, where we tend to overestimate progress in the near term and underestimate progress in the far term, and I think that that's probably certainly valid here. Okay, a disclaimer. As I said, there's a huge body of literature on Moore's law, 16,000 papers since 2000 alone, and by people who are far more cognizant of what's happening than I am. I can only see one part. I'm like the 10 blind men who look at an elephant. You look at one piece of it and believe that you have the whole thing, and you don't. And I think Kai gave a very good indication of my background. I've been involved since the late 70s, and I've kind of grown up with it. I got my first computer in the early 1980s. And have followed Moore's law, a new computer every 3 years since then, and it certainly has improved my productivity. So if I miss your favorite perspective, please chime in. There's a lot of different ways of looking at this. So probably the best thing to do is to take a look at what Gordon Moore said, and I think there's a IEEE Spectrum article from 2015 where he reflected on the original 1965 paper. And basically what he was trying to invoke was that electronics was going to get cheaper and it was going to be more powerful. And he wasn't really thinking of it as some hard and fast, things will continue down a particular road path. He was just trying to convey that we're going to get more digital stuff. And so that, in fact, has, from a societal point of view, Moore's law has just become a shorthand for more powerful processors and generically greater productivity through digital stuff, whatever that may be. And that certainly has been the case. I think as the pandemic has demonstrated, and the fact that we're on Zoom, that Moore's law's impact on the world economy cannot be overstated. You can't ship cars if you don't have chips, and they've had a hard time getting chips. So that's, and it's not just, I tried to buy appliances here a few months ago, and that turned into a real nightmare because they couldn't get the chips for the appliances. So, you want a refrigerator, stand in line. I would also make an observation that the highest volume products do not need the latest process. So you can build a TV remote clicker without using 5 nanometer process. And in fact, if you're familiar with Texas, up in Lubbock, there is a foundry called XFab that is great at making chips at 350 nanometers and 180 nanometers, and they seem to be going great guns, because a lot of things don't need the latest and greatest process. So let's talk about the impact on productivity here for a second. There's an old saying, a rising tide lifts all ships, and that's true of productivity. Improved productivity generally translates into an improved standard of living, and more people can do fewer things, fewer people can do more things as a consequence. And if you look at modern society with cell phones, GPS, industrial automation, that certainly has been the case. And so obviously we can't cover all of that. So the typical thing to do in a situation like that is to choose one aspect and maybe elaborate on that. And what I've chosen is agribusiness. We all like to eat, and we get our food from agriculture. So if you look at the US population involved in agricultural employment at the turn of the last century, it was about 17%. And that's farmers plus people who were involved in hauling grain or building tractors. if you look at it in 2020, there's actually much less than 2% that are involved. Now then, being a good engineer, I recognize there's more people in the US in 2020. So if you multiply it out, it's still less, plus they're producing far more product. And so I wanted to describe that from a couple of perspectives. One is the modern tractor. I don't know how many people here are familiar with agribusiness and tractors, but they're more like spaceships than they are tractors. You know, we have this vision of old MacDonald in his tractor, and you know, he's sitting on this tractor from, you know, the last century. Nowadays, they sit in an air-conditioned cab. They're autonomous driving. The operator doesn't really have to drive the tractor. They sit there and look at their cell phone and play solitaire. There's a lot that goes into precision planning, where they actually, both in planning and in harvesting, they are familiar with where they are on the land and what is the water requirement, moisture requirement, how much pesticide, how much seed that they can plant in a particular part of the field. And then in harvest, they do precision tracking of how many bushels of corn, for example, that they get on a per yard basis, what the moisture content of that corn is, or soybeans, whatever it is they're harvesting. The tractor itself tells you and will actually call the factory if something is starting to break down, so that the uptime of the tractor is much higher. And not only does it do the tractor, but it will do the farm implement that you're pulling. If you have a seeder in the back, or you're harrowing or doing any of the other processes, it will tell you if you're starting to experience a failure with one of those implements. And if you're not familiar with this, one of the areas where you can take a look is on YouTube. There's a guy called the Millennial Farmer. He has a channel. If you've never seen it, it might be worth your while to go and look at one of his harvest videos, where on a daily basis, he describes the problems that they run into in harvesting, and, you know, how the tractor operates. And so it's interesting. He is in Minnesota. He's preparing to get ready for planting right now, and you can look at what goes into that. And then you can look at last fall's harvest, or one of the previous years. I think his previous years may be a little bit better, but I suggest, if you have the opportunity, you take a look at that. And I have in the references at the ending of this some of these videos that you might be interested in following up with if it floats your boat. Another sort of thing is there's a woman, and actually she's a 17-year-old who has a YouTube channel called Kate Zag. Her name's Kate Stevens. She's in Montana. Her family does wheat farming, and so she's learning the farming business. And in some respects, it's better because it's she's showing the viewers as she's learning to do these. And recently, like within the last month, she went up into Ontario and did a video on apple harvesting. And that was, I had no idea the technology that went into apple harvesting, from the mechanism used to pick the apples, to how they sort the apples, how they sort them based upon the type of apple it is, whether or not they have blemishes, the size, and they're able to track the apple from the orchard all the way to the grocer with which they send it. So food tracking is an important part of the grocery process these days. I have her video in the back as well. And then African farmers, it's made a huge difference with them just by having cell phones, because in the past they would make a crop, and by the time they harvested the crop, that crop may not be valued, that everybody may be making the same crop. And what they're able to do now is, even though these farmers do not necessarily have electricity on their farm, they can walk into town, connect up to their cell phone with a buyer, basically sell their crop with crop insurance, go home, grow the crop. The purchaser will send the packages. They load the packages and then send them to the end user. And as a consequence, it's more or less guaranteed the income that they get for farming. And it's made a huge difference in their standard of living, because now then that they have a stabilized income, if you will. So that leads me to Moore's Law observations number 2. And there was an interesting IEEE Spectrum article, I think last month or the month before, where they talked about the fact that a modern laptop has 10 to the 15th times as much raw computing power as the IBM 7090 built in 1961. And that's pretty hard to digest, that your basic laptop has that much more power than what they had in 1961. And in addition, when they did this, in addition to the raw transistor count, they also took into account architecture improvements, multiple cores, etc. So there is circuit innovation that's occurred as well. And as time has gone by, that circuit innovation has become more important and is needed to take advantage of all the transistors. And my own experience in talking to people at the International Solid State Circuits conference here a few years ago is that the circuit, the gate length on a FET is becoming kind of meaningless as a mechanism to measure the power of a process. And that has been going on for some time. If you look at traditional scaling, which is using silicon dioxide for the gate, that basically died around 2003. And I'm sure Lawrence can chime in on that, and that he's been probably much more involved than that. So finally, if transistors don't get smaller, the chips are going to have to get bigger. So we'll address that aspect. So bear with me a second. If it wouldn't be a Moore's Law presentation if we didn't look at the history of the devices. And basically what I've done is I've plotted, the easy thing to do is go to 2020, which is when 5 nanometer devices were started selling. TSMC says that they're going to be selling 3 nanometer here pretty soon. In a couple of more iterations, you're down to the size of a single atom. I think at that point we can probably declare Moore's Law is dead. If you look at it strictly from a scaling point. If you look at it from a productivity point, maybe not, and we'll go into that. So Moore's Law dead. That would only impact a small part of the overall electronics industry. There are billions of transistors available for circuit innovation. And I think it was kind of interesting that in March of 2022, Advanced Micro Devices here in Austin had a greater market value than Intel, and AMD is fabless. So, that was kind of an eye-opener. So I wanted to go into chip building. I don't know how many people here in this group have been involved in building chips. I've had an opportunity to cover it from a foundry as well as through a design center. And it's kind of an interesting process that you don't normally see. So first off, thermal management. In the 1990s, we reached a point where around 75 watts, I guess, at 4 gigahertz clock frequency, they pretty much maxed out, how much they could drive a chip without going to extraordinary cooling measures. I'm sure many of you were watched that unfold. There are the so-called overclockers for a while. If you went to TARM's hardware, they would teach you how to overclock your device. Nowadays, I don't think they do that because the device manufacturers basically took advantage of that to do turbo modes on their chips. And then the one that probably was the first nail in the coffin to Moore's Law was the fact that when they got down to about 90 nanometers, the gate started leaking because of the thinness of the silicon dioxide. So they went to hafnium oxide to strengthen the gate, and that was probably the first big deviation from standard or traditional device scaling, so to speak. And again, some of you there may have far more insight into this than I do. But because of the leakage, again, it required some extraordinary measures and more cooling. So not knowing the range of people who were going to be involved in this, I think one of the unsung heroes of Moore's Law are the people who put together device models. The traditional planar FET, like shown on the far left there at the bottom of the screen, had there was a relatively well-known model that could be tweaked on a process node by process node basis. But as you started going into FinFET, represented by the second from the left, it became more difficult to use those standard models, and they went with more empirical models. And the problem that you run into is the switching speed of the device. In every process, as good as those processes are in terms of being repeatable, there is variations that occur. And so you have what's known as a slow process or a slow device and a fast device. So between P and N devices in a CMOS circuit, you can get slow, slow, fast, fast, slow, fast, fast, slow for each of the devices, and then nominal, nominal. And I tried to capture that by saying, okay, let's imagine an automobile where the engine gets smaller every year, but the miles per gallon that varies by the engine. So in the initial year with the standard engine, you maybe get 30 to 32 miles per gallon, but each subsequent year the engine gets half the size, but there's greater variation in the miles per gallon. Ultimately, as you went to 2040, 1050, or maybe 560, it would become impossible to use that engine because you could never predict how much gas you needed. You might be lucky and get something that gets 60 miles per gallon. You might get unlucky and get something that gets 1 or 2 miles per gallon, which would be useless. And as the gate size shrinks and you're down to just a few number of atoms, those statistical fluctuations get worse. And the single most gating item in a digital IC development is called timing closure. Hopefully most of you are familiar with that. And the device model has to be tractable in the sense that if you're going to be using it on a device that has 100 billion transistors, it needs to be relatively fast. So this is a block diagram. It's not comprehensive, but I would say generally representative of timing closure. Normally that's done under what's known as PVT, which is process voltage and temperature. In the old days, back when I was designing chips, there would be a chip architecture. You would get an electrical and functional specification. And then when you had the chip designed, using Verilog or some other tool, then essentially you would throw it over the wall to the layout people. And that's where things got ugly, because they would have to do timing simulations based upon some test patterns. They would do what's known as LVS, DRC, and ERC, which is design rule checks. And then they would characterize for PVT. And most of the chip would work, and maybe 5% of the chip wouldn't work because it wouldn't pass PVT. So now you have to go and iterate the whole chip just to accommodate the changes of those few gates that weren't working and do the whole process over again. And more than one chip has taken many months to get out the door because of this iteration that had to be done. And so there is Synopsys, which is one of the main companies that provides tools for this, is claiming that they're using machine learning to help meet timing closure. I'm sure some of this has changed. They've recognized that throwing it over the wall to the layout people isn't going to work. So it's a more holistic process these days. So where are we then? Let's take a look at the near future and some productivity improvements. As I mentioned earlier, TSMC is shipping 5 nanometer devices, and they claim that they'll ship 3 nanometer in 2023. And this is qualified in that they don't claim to be shipping in volume anytime soon. Most device builders are using all those extra transistors to build products with multiple CPUs and GPU cores, and also what is known as there are other coprocessors that are being developed to take advantage of the higher transistor count. In the old days, desktops and laptops were the drivers for processor improvement. These days, it seems to be Bitcoin mining and gaming are the drivers. If you look at other high volume products like cell phones and laptops, they're really beginning to trade performance for battery life. So being high efficiency is more important for battery life than necessarily the fastest performance. So to use that as an example, if you look at last year, Apple introduced their M1 ARM processor. I don't know if you've had a chance to look at this, but the Apple M1 is done in 5 nanometers from TSMC. It has 8 CPUs, 4 for performance and 4 for power, 8 GPUs, again, 4 for performance and 4 for power, and then a 16-core neural engine, which is used for machine learning applications. My expectation is that there will be other coprocessors that have been added, and I noticed in their most recent incarnation of the M1, they've added a media processor as well. And I'm not exactly sure what the media processor does in addition to a GPU, but it's another core process, another coprocessor. And I would expect to see additional ones. So one would ask, well, where will that end? People have done processors with up to 1024 cores, and at some point the performance goes asymptotic because of the communications problem in talking to all of that. And we'll get maybe a chance to address that near the end of this presentation as well. Hold on just a second. So one of the things that's happening in our industry is a movement to cloud computing. With cloud computing, you can use the latest processors and you can run them at their highest speed and basically cool them. A lot of people put their computing centers in Iceland, where they take advantage of a lot of cold water that is available there. For mobile remote users, they can be relatively low CPU intensive, like a Chromebook, basically built for battery life as opposed to power. And I would point out that the weak link in all of this is communication. In order to use the cloud computing environment, you have to be able to communicate with it, which means that you really don't want to live in a rural area where your connection to the internet is pretty low. But then maybe again, that will be served by Starlink. We'll see. There's been a resurgence in asynchronous logic or clockless logic. I happen to be involved in a clockless logic startup, and that was about 15 years ago now. And so it begs the question, where is clockless logic? At that time, we were building clockless microprocessors. We, as well as a range of other people, including NXP, there was no take-up for these devices. If you look at modern logic design, it's focused on synchronous or clocked logic, and it's hard to get, once you're in that mindset, it's hard to get people to think outside that mindset. That said, there were several startups here in the Austin area that were working on clockless logic, and they seem to have been bought up by some large companies. I won't name any names, but there's reason to believe that there may be some clockless logic in some of the latest processors used by a rather large fruit-named company, as yet unnamed. The Internet of Things, there's a lot of talk about the Internet of Things, and I think that will happen. Again, the object there is to put low power devices out at the edge, do computing there, and then through a very massive communications capability, bring it to storage areas where that data will be operated on. I think that this is a variant of cloud computing, and I don't really see that stressing the processors that much. Software-defined everything. I happen to be involved in one of the original software-defined radios in the late 80s. What's happened subsequent to that is that software-defined radios have taken off. They've become commodity products now, and as a consequence, there are people that are talking about developing generic digital hardware and personalizing it through software as software-defined networking, software-defined storage. You can carry that into whatever particular product you're involved in. Is it software defined by using a common set of hardware, and the functionality is defined by the software itself. One of the areas which is starting to raise its head that makes me squirm a little bit is device as a service or subscription-based hardware. This is a growing movement to make hardware subscription serviced. So it would be you bought an 8-cylinder engine, but you can only use 4 cylinders unless you pay an extra subscription fee. Intel has plans for developing subscription-based processors that are along that line. How much of the processor you can use depends upon how much you're willing to pay at any particular moment in time. And there's for those of you that are old enough like me, you might recall that this was done by IBM in the 1960s with their printers. You had a high-speed printer and a slow-speed printer, and the only difference was which geared wheel the chain was attached to. So whether or not you paid extra for the high-speed printer depended upon whether or not a technician came out and attached it to the high-speed wheel versus the low-speed wheel. So let's take a look at the far future. 3D processors. There has already been a movement, and I think there are already devices that you could purchase that integrate several layers of devices. And as I said earlier, if you're not making transistors smaller, you need to make the devices bigger. And the 3D processors is one mechanism for going down that path. While this increases the number of components, it doesn't address fundamental thermal and signal wiring limitations. So there is a great deal of research that's going on to address those kinds of issues, particularly the thermal issue. One that I like is the integrated non-volatile memory. And this slide is going to take a few moments to explain, so bear with me. The object is that instead of having cache and storage, memory and then storage, that you just have one very large non-volatile memory that's fast. And one way to look at that is you can find on the web these normalization charts, and the spreadsheet at the right is an attempt to do that. It takes a look at it normalizes the basic clock of 250 picoseconds, or about 4 gigahertz, to 1 second. And then from that, it then extrapolates what is the time associated for each function, like an L1 cache reference, or reading memory, or sending data over the internet. And if you look at the red enclosed reading 4K randomly from an SSD takes, and unfortunately it's 6 days. And to read 1 megabit is 46 days. So compared to 1 clock frequency, that gives you a feeling for how much time is lost in trying to make those reads. If I could make one memory that is a terabyte in size, and whether or not it's storage or working memory depends on logical reference as opposed to a physical reference or an electrical reference, I could greatly speed up how my computer operates, because I'm not wasting 46 days. I'm doing it in 1 or 2 seconds. So there is a movement to make in terabyte non-volatile memory that's both fast and used for that purpose. And I think that that would actually be a huge improvement for processors. Non-conventional computing. Again, this is pretty fascinating. For certain processes like machine learning and AI, they actually use, when you look at how it's done, you can use a non-volatile memory to do that. And there is a startup here in Austin over on Metric Boulevard called Mythic AI. I don't know if anyone here is familiar with them, but they're attempting to do just that using non-volatile memory. There is a excellent YouTube video put together by a guy named, well, I don't recall his name, but his channel is called Veritasium. I've recorded it in the back, and if you've never seen this particular video, it's actually quite fascinating. It's about a 15 or 20-minute video in which he came to Austin and went to Mythic, and he kind of explains the whole process and why this startup actually has a fairly good chance at success. And so the belief is that analog computing will dominate certain classes of problems like AI and machine learning, and probably added as a coprocessor to existing processors. DNA computing. People have demonstrated DNA binary memories and higher level logic memories. It has the potential of being a huge memory storage. I don't know about its potential as a processor, but they seem to be working in that direction. So, you know, is Babelfish going to be a reality? Perhaps. I find this both absolutely fascinating and potentially disturbing to think of where DNA computing could lead. You know, will you attach something to the back of your neck and, you know, we'll just get used to having these computers bonded to us? I don't know. The possibility is there. Finally, there are other non-conventional computing techniques, optical computing, quantum computing, molecular computing. All of these different techniques are still in the very early stages. You can't buy one, and they all appear to be useful for solving specialty problems, particularly highly parallel computing type problems. Whereas the DNA computing looks like it may be potentially possible to do a general purpose computer with it. So one of the things that becomes interesting is to see if there's any economic models that we can appeal to see where electronics may be 20 years from now. And one that you can look and read about on the web is steel. If you recall the history of steel at the end of the 1880s, 1890s, they started mass producing steel, and as a consequence, it began to impact particularly the United States, but all across the world. You could build steamships. Railroads had their moment where railroads became the Silicon Valley of the day, and people were making large sums of money funding and building railroads. Skyscrapers using steel frames were invented. internal combustion engines could be built because they had quality steel. Plus they had specialty steels like stainless steel and things like that. So if you believe that electronics will go down that path, I don't think it's going to be as static as steel because there is a continued potential for circuit innovation, but it may become asymptotic like steel did. And so what's the far future going to look like? I think computers and embedded processors that we know today will perform marginally better. I think that the human interface will
Well, I can go in the, I got it set so that I can go in the dining room. I'll do that.
Okay. I'm upstairs. Co-processors, this is the last two slides. So we can bring it to closure here. I think that the human interface will be more sophisticated. I think that there will be numerous co-processors invented and available to accelerate certain types of solutions. I think that the chip industry itself will become stable with fewer players, bigger players, and I think that there is a desire after the pandemic for every major economic bloc to have their own domestic suppliers to avoid some of the dislocations that occurred during the pandemic. I think that there will be continued innovation, particularly in circuit design, processor architectures, communications and control interfaces, which are becoming increasingly important and certainly are the driver for things like IoT and cloud computing. So the final slide here. This past week, about 10 days ago, I went to the Apple media event that they had, and one of the things that they revealed was what they call their M1 Ultra chip, which was basically just two M1s tied together through a 10,000 high-speed interposer chip. The M1 Ultra uses 114 billion transistors. And they claim that because of the co-processors and the number of processors that's used, that it will just use forced air cooling and will be really quiet. There possibly could be some barrier that we're unaware of lurking in the grass. Hard to say. I think that there is a huge opportunity in our business for innovations in architectures and circuits to take advantage of all of those transistors. And I think the focus will change from huge investments in building transistors to huge investments in making things smart. And with that, I think the final slide is the references and resources, which if someone wants me to send it to them, I would be happy to send it to them. And with that, Kai, that completes this. No questions, I gather.
Oh, thank you. That's a very good talk. Yes, you can send your slide to me, then I will post it in our website.
Okay.
You can get those reference. So just wanted to add, I think quantum computing is available for hire. I think IBM and AWS, Amazon, they offer that service for timeshare. You can buy some all the time you need to run your special program.
Okay.
But the application is still limited. Maybe good for certain area, but not a broad-based use. They still need to build a lot of stuff, you know, work software and things like that. But,
so I would think maybe Lawrence would have some insight to add.
I'm already unmuted. Okay. No, in fact, I'm sitting back here muted, cheering, because I'm pretty much directly in line with your observations. Sort of fun, just by accident, I wore my Semitech t-shirt today. And And so, my personal struggle was, making the actual devices smaller and high K and all that good stuff. I will note in my memory, I think Moore's original quote dealt more with functionality than with transistor size.
Mhm.
And what you just presented, smack on. Although I agree, it's getting tougher and tougher.
All right. Oh, by the way, for software-defined radio, originally we called it synthetic radio. And there was a fella at Motorola that in Arizona that coined the software-defined radio, and that stuck.
Yeah. Well, regarding Mythic AI, I think they were speaker when they first come to Austin. Probably I need to revisit with them to update what they do.
Mhm. Actually, there was a question, as the devices get smaller, do they become more susceptible to cosmic rays and other radiation? And that's a real concern. And there is reason to believe that a number of different computer failures in recent years were the results of single event upset. And as they get smaller and smaller, obviously they'll become more and more susceptible to those kinds of perturbations. So maybe that's one of those barriers lurking in the tall grass that will jump up and bite at some point. I think there is a recognition of that and some concern, but I don't think there's been an industry response to that at the moment, unless somebody knows something. Okay, is there any more?
There was another question in the chat that came in a little before that.
Oh yeah, how thick is?
How thick is the M1?
I have no idea. I was pretty impressed with. I was impressed with the 10,000 line interposer. You know, to be able to do that, a high-speed interposer to make two chips, and apparently, act like one chip, and just awed by the number of transistors that are on those two chips. So, actually, what we should try to do, there's a fellow here in town, Mike Sinnigan, who works as a transistor wrangler for Apple. We should try to get him as a presenter and see if he can elaborate on that. He might have insight. I don't know.
Yeah, well, probably Apple don't allow this.
Yeah, that's a possibility too.
Yeah, we tried that before.
Oh, did you?
Yeah.
Okay.
Something you said about the one of the old problem was timing closer. Can you explain a bit more about that? I am a product engineer, so I really don't get into that deep in the circuit.
When you develop the physical layout of the circuit, and then you run your tests on it, you don't know whether because there is variation in the silicon, you may have slow transistors, slow P transistors and fast N transistors, slow N transistors and fast P transistors. You don't know. There's some variation that the process allows. And what you have to do is you have to test it, because any feedback loops that you have that, you calculate some value and then come back and feed it back in, those have to settle out, and they have to settle out before the next clock strikes. And if they don't settle out, then you'll get a race condition. You'll get the wrong answer. And so they have to do that under all conditions of temperature, voltage, and process, slow and fast. And as the variation becomes higher, it becomes more and more difficult to get that built in. And recently, Intel missed its date for supplying certain processors that they were going to supply. They didn't really go into detail about why they couldn't supply it. So it's undetermined whether it was a processing problem or whether it's a getting the chip to work under the conditions of PVT. I got $5 that says that they couldn't get the chip built under PVT, that they could build the transistors, but that they couldn't build it under PVT. And if anybody wants to take me up on that, then you know.
Well, I think that's always the case. You work on simulation.
Yeah.
You need to really test it under stress condition. Maybe they did not put enough time delay in some of the circuit or something like that.
But I having been there and done this before, it's hard, a lot harder than people realize.
Yeah, I mean, in the old days in Motorola, where we work, we only have a limited customer. So what the big chip we deliver, we only have a few companies who help us to debug. So we get a $1 per month or $1 per week when the first silicon coming out.
One of the advantages of clockless logic is that, you know, in a clocked logic, when the clock strikes across the chip, things start switching. And when things start switching, the chip starts drawing power. And so there's a lot of power draw every time the clock strikes. If you have a clockless logic, things are spread out. It's not a impulse, so to speak. It's spread out over a longer period of time, and so it puts less stress on the power supply, which is another thing that's difficult to do on modern chips.
Yeah.
And Dennis, that's an interesting point. This is Bill Martino. Do you know which companies are using artificial intelligence and machine learning to reach timing closure now?
Yeah, Synopsys said that they're doing that.
Ah, wow. Okay, so that opens it up to a lot of people.
Yeah.
Yes.
I think that's cool. All right. Yeah.
They said that they were using machine learning to help do timing closure, and I thought, wow, that's a good use of machine learning.
Yeah, I like that a lot. Thanks.
Actually, today I was daydreaming. I thought PLL was one of my my career contribution for digital phase-out loop.
Oh, really?
It's in every device, right? Now it's going to string everything. You put a little module there. But before I do the standard PLL, but now you say the cordless logic. That means we do not need any phase-out loop.
Well, you still have to get on and off the chip. I mean, the rest of the world is going to be clocked. So, you know, basically, I think what Apple is doing, and this is just wild speculation on my part, is that there are certain parts of the chip that are clockless, and through mutexes, they go into the clocked parts of the chip. Okay. So that would be my speculation.
Well, I think you're right. We still need some basic timing functions. Mm-hmm. But in certain area, you can go clockless in certain areas. Yeah.
So, was there any other questions?
Yes. No? Well, that's a very good topic. Much.
I hope
more information than I expected. That you corrected. And actually, yesterday I was in attending a event in a Capital Factory. They talk about quantum
computers.
Yeah, quantum in theory. I mean, in general, there's a lot of interesting thing going on in the quantum area. A computer is just one of the things. Yes.
Kai, I just changing the subject on you real quick. Originally, when we talked, one of the things that we talked about was SpaceX and McGregor, Texas. Yeah. And I grew up in McGregor. Go there quite a bit. So I can tell you about McGregor through the Rocketdyne years, because that's where my dad was employed. And I have prepared a presentation on that. So sometime this fall, when you need a presentation, I'd be happy to share some insights on SpaceX in McGregor, Texas.
Okay, great, great. Yeah, actually, we try to hire somebody from, find somebody in Tesla to talk about whatever, either the vehicle or the Boring or the SpaceX. So you can,
This fall, I'll be going to my 50th high school reunion.
oh,
And
okay.
the good thing is the constable is a buddy of mine because we went to high school together. So,
Yeah, okay. Maybe you can take some good picture there.
yes. And I have the other thing is that IEEE gave me my 50th 50-year
Uh-huh. Oh,
thing, 50 years with IEEE, because I joined in 1972.
all
So
right.
I didn't really want to tell you how old I was, but you can figure it out now.
Yes. Yeah. Well, we're quite a lot of senior members in this group, the Life Member. Yes.
Right.
Yeah. So, well, thank you very much.
Okay.
Any question from the group? I think there's 20 people remaining.
Okay. Well, thank you for your kind attention.
Yeah, thank you. So we'll see
Thank
you later. All right. Thank you very much. And everyone have a good evening. Well,
Yeah.
come back to Austin.
Take care, everybody.
Okay.
Have a good
Bye-bye.
Bye.
Let's see. Hmm.